Okay. So first thing I will say is that I will go a little bit faster than normal, and I will skip some stuff because most of you know about this, and so all the motivation I will go really quick. So this is the typical idea of how do we get to know the emergence in general and self-organization, and so there are like one idea that is relevant to this is thinking of emergent systems composed as some pieces. So they are not completely disassembled and then all of a sudden everything is emergent. There are some sort of substructures that play some role in between the emergent structure and the parts. There are certain intermediate sort of fragments, like in the ecosystems we have trophic levels, or in economics we have specific markets, or in politics we have divisions in between, which is not the politicians, it's not the whole political system, it's just like some sort of vague intermediate parts. And these are an important part, because when we are looking at what Francis was speaking in the previous talk about perturbations to this self-organizing system, so the focus of this talk is mainly in the idea that when you make a perturbation, we can define perturbations kind of precisely, but perturbations do not just perturb the system. There is something more you can tell about the perturbation, which is it perturbs a specific fragment of the system. And how do we define the boundaries of where the perturbation is making an impact on? So that's kind of like the not really. So that's what I will be trying to advance some ideas on. And it's a sort of mathematical, or let's say structural analysis, which does not in principle make a definition of resilience or of degeneracy or all of the other sort of mechanisms that make a system more resilient, but brings a sort of structural analysis layer, which will allow to make such definitions. So it's just like creating a conceptual layer on top of which we can build these ideas such as degeneracy, resilience, and so on. So we got the reaction networks on one side, and yeah, but I will go really quick. So this is another thing that when we think of this reaction network and this feedback and the self-organizing system that Francis was explaining, and the basin of attraction, like the phase space view of it, we can find that if we think of these fragments, of these parts of the self-organizing system that are some sort of vague pieces of it, and we can have a hierarchy of them. We can have very small things that we consider to be fragments. And it's interesting that within the larger system, this smaller fragment have a larger system environment, because we have the whole thing, the whole universe of interactions, and we have the focus on our system, which we say, okay, the system receives inputs and brings output to the outside. But within this system, we can have some inner parts. So these inner parts of our system, if we take smaller parts, then the whole system, it must be like a larger environment for them, within the existence of them, plus the other larger environment, which is the one of the environment of the system. So we kind of have this hierarchical notion of being, because then the system, the self-organizing system, is just where we are putting the focus on, because maybe the parts of the system are also self-maintaining, or are also operating in this way. So where do we put the boundary to say, this is the system, these are the parts, what is the real self-maintaining thing, or what is the entity, right? from principle, from the beginning. So, okay, I will not go deep into this, but I think that this hierarchical notion of being, that we say, okay, we have a self-maintaining, which is embedded in another, and this connects with different, if we put these pieces together, we get a larger piece. So we don't have a real kind of very concrete place to put our fingers on and say, this is the system. We have a sort of hierarchical mass of things that behave in self-maintaining ways. And then I think that it makes complicated to make to speak about what is identity, what is agency, or what is purpose. So our approach, of course, in this grant is to try to move towards a more operational way, so we can make concrete and strict definitions, and so clarify maybe some long-standing debates. So I will go to the quickly to the idea of reaction networks. We know what a reaction network is. Francis explained it very well. And since we are not dealing, and this is the important thing, we are not dealing here with the traditional dynamical analysis systems where you have three equations. I think I have a slide for it. Yeah. So the typical system here, like you can see here, the reaction one tells you S1 is brought from the environment, from the outside. R2 takes S1 and S2 and makes out S3, and that's it. That's all what we have. The initial conditions are we have a lot of each of the things in the beginning. I don't have units here, it's just 100, like a lot. I'm saying like not, because when you have very small numbers, certain particular effects can happen. We have studied that in the past, but I don't want to go into those specific technical details. And then the interesting thing is that we have this reaction network, and we need to tell some sort of way in which it will react. So the most typical way of establishing how things react is called the mass action kinetics, and it makes a lot of sense in chemistry because it assumes homogeneously distributed and isotropically moving molecules in a vessel. So we just have everything super well steered. Yeah, super well steered up. And then we can build our differential equations. So this S1 dot means the change in time of molecule S1. There is this K1, which represents the happening of reaction 1 in time. And I make it as an explicit function of time because it might be a constant value, or it might be a periodic function. For example, if it will be sunlight, we know it's not constant sunlight, we have a cycle. So that is probably a periodic function and so on. And then K2, S1, S2 represents the happening of S1 and the probability or the extent at which S1 and S2 will get together in time. And then if you multiply that by K2, which can be the rate of success of the interaction taking place, or the speed of the reaction, there are multiple interpretations depending how is our specific model occurring in space-time. We will have that S1 is consumed by reaction R2 at this rate, and then we build the rate for S2, which is just simply being being used up by R2 at the same rate at which is used by S1, because they both participate, and the guy S3 is getting benefit of it, so it has positive rate, whereas the other two have negative rate. So this is very simple, and we have here slightly more complicated reaction network. We will have something that we cannot solve. Wow. Hello, can you hear me? So I got freezed. Yeah. Do you see the camera moving, or am I freezed?
No, camera is frozen.
Okay, I will restart the camera then. So stop video, start. Can you see me now?
Yes.
No? Yes. Yes. Am I moving?
Yes. 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 You're moving.
Okay.
Yeah.
Because I see myself freeze, but you just don't bother to let me know by the microphone if there is any problem, because this I think we have some sort of processor unit tiredness.
Okay.
It's kind of making noise like leave me alone. So yeah. Okay. So I continue. So what's the problem with this system of equations? Is that this approach has been done by many people. They study nonlinear dynamics and phase transitions and hysteresis and tipping points and catastrophe theory. And there is a lot to say about this system of differential equations, and it's very interesting, but it's not scalable. If we go to really complex systems, to hundreds of dimensions or thousands of dimensions as it is in biochemical systems, we will not be able to do anything about it. It's just too confusing, too many parameters. There is no actual way to say something reasonable about it. Instead, if we think in terms of ending sets, like in attractors themselves, and not in the specific form of the attraction of the attractor, if it's going to be a limit cycle or a strange attractor or a fixed point, we might not even care about it. We just want to know which guys will be sticking around after a while. And we might not even care about the constants as well. So that's why I say for this structure, we will end up in the set S1, S3 for any reasonable choice of the kinetic parameters. We will not really end up anywhere else. There is no, because as you can see, S2 will be used up by R2, not reproduced back. So S3 will be generated out of that, and S1 is always constantly generated. So we don't know the specifics of what are we going to end up with, but we know that that is going to be the reaction network we end up with. But now, this idea of thinking of mass action kinetics might be interesting, but not the only one we can do. And especially if we are modeling conscious systems or ecological systems or some sort of decision making and some sort of inner goal of particular elements of our system, we can choose, for example, that mass action kinetics, but there is a control system that if S3 is larger than 25, just to give a number, then the second reaction will not happen anymore. So we know that the system will evolve like very naturally, but we have a sort of person measuring, detecting how much S3 there is there. And when there is more than 25, it just shut down as R2. How it does it shut down, we don't care. We might create mechanisms for that, but just for simplicity, we don't care. And in such a case, we will end up with the set S1, S2, S3. And now if we add the reaction, we bring another person who says, let's say an evil person who says, okay, I'm gonna try to kill R3, S3. So I bring this reaction, I create this reaction, I put it in the system. Then if you add the reaction R3, which is explained there, you end up in the set S1. So the evolution, the time evolution of the system will end up in different situations depending on the structure of the network and on the way the network is operated. So people in graph theory and network theory, they tend to think that the structure of the network is all of it. But the angle that I want to make very kind of clear is that the way the network is operated, the way we choose how reactions are going to take place is a very big choice for what we can say about it. Okay, so this is important to clarify, because all these mechanisms of resilience might be structural for the network, but might also be depending on how do we apply the reactions, what are the choices that we allow for it. Because most people in this field tend to think that mass action kinetics is the true, or saturated kinetics is the only two ways to go. But we can have very different algorithmic forms of operation of the network. So yeah, okay, so now we say, I will go very quick on this because you all know. The first thing to know is that if we have a set of reactions and a set of species, every time we take a subset, we activate a particular set of reactions. So this can be formalized, and this is these are very simple examples. The only, in this case, we have only one reaction. So of course, once you have A and B, you will have the whole thing. And then we define what is closed. If all the produced species in the reaction set are in the set, and semi-self-maintaining if every species consumed in RC is produced in RC. That's semi-self-maintaining, and it's not entirely self-maintaining because it can, I have some stupid examples here, but semi-self-maintaining is important. There is not self-maintaining because you can be able to topologically reproduce everything, but not in the right amounts. So the typical example is A goes to B, 2B goes to A. With 1A, you generate 1B, and then in order to recreate that A, you need 2B, but you can only produce 1 out of 1A. So the cycle is semi-self-maintaining, but not self-maintaining. So then in order to define self-maintenance, you need to go a little bit beyond the simple topological structure of the network and need to look at the processes that can be applied. So how the pathways, let's say, that can be applied. So we introduced this notion of process to specify how reactions will occur within a certain time interval. So what the process brings in is a collective transformation of a species. So all these reactions are going to happen. So all these things are going to be used up and all these products will come in. So it's a sort of collective transformation in the system. It's a generalization of a reaction, basically, for the structure. And I got here a simple explanation for self-maintenance. So A plus B goes to 2C, B plus C goes to 2A, A plus C goes to 2B. The process R1, so considering that only operate the first reaction and the other two gets kind of like dormant for the moment, that will consume 1A, 1B, 0C, and produce 0A, 0B, and 2C. If you go through the process R1, R2, so first reaction and second reaction, you will be using 2Bs because one from the reaction R1, one from the reaction R2, 1A and 1C, and you will produce 2A, 2C. And the process R1, R2, R3 consumes all that and produces all that. So then we get the self-maintaining process. It's not that the system is self-maintaining, it's that there is a process under which such a structure can self-maintain. It's a completely different thing to keep in mind. So a process is self-maintaining if and only if produces the same, can produce. So the process is self-maintaining, produces the same or more than what consumes. And there is a specific extra consideration that everything that can happen must happen at some rate. You cannot just shut down a reaction because it's good for you. You need to say, okay, everything. So that's an important constraint. And the interesting thing is that this can be defined in terms of linear algebraic terms. Particularly, this is a linear programming problem. And these solutions will be independent if we use mass action kinetics, saturated dynamics, or algorithmic dynamics, whatever. We just identify the potential of the system to self-maintain. Later, if our rules allow for those processes to happen, to be those that actually happen, then the system will self-organize. But this is a sort of a linear algebraic embedding of the possibility of the system to be eventually self-maintaining. And then an organization is a set, as was defined before, that is closed and self-maintaining. And we know, Stefan Peter will take the stage in a few minutes to talk about more the specifics of how do we connect organizations with stationary states or limit cycles and all that, in both in only time dynamics and time-space dynamics. So there is a whole line of research connecting these structural ideas with the real dynamics, dynamical rules, and continuous dynamics, and making like really concrete, let's say, steps towards dynamical systems theory. But I will just stick around in the abstract world. So what we have is a reaction network. Then we have an abstraction of the phase space, which is all the possible subsets which correspond to all the possible subspaces of the phase space. And then what we see is just discard. This is not closed, this is not self-maintaining, this is not. So we end up with the green guys, which are the organizations. And these are the regions in the phase space where we can eventually find attractors and all that. So then the general overall dynamics, taking off all the complexities of the nonlinear dynamical systems, will be just moving from different organizations by perturbations that trigger those changes. And the notion of a structural change, which was introduced by Francis, and it's the idea of adding new reactions, is just creating a perturbation to this. It's called Hasse diagram. For those who don't know it, this is the Hasse diagram. So if we bring in a new molecule, let's say X, we will have to create a new line here for each of these objects. We will create just one-dimensional extra thing, one more for each of them. And then we will restructure with what are the organizations in this new thing. So we have some sort of change, some sort of derivative. If we add something, if we have this, let's say, has a diagram, and we add a small perturbation, let's say a new reaction, we will just get a new partial order set, new Hasse diagram, which might look a lot like the first one. It's very strange that we will expect that in all possible cases, small changes will lead to major changes in the in the parts of this structure that are the organizations. So that is what we have in mind. How do we move? How do we change this partial order set, adding perturbations and maybe keeping certain properties? That's maybe the mindset, but never forget that this is constrained to the happening of the reactions, which is also a choice we must make, how reactions happen. So algorithms for this, which is a little bit what I will talk today, I call them tractable, because they are tough, but they are still tractable. So we can, the idea is that we can make use of structural results or analyzing the general properties of the reaction networks to make algorithms that can identify these structures and so on. So this creates a sort of toolbox for defining resilience, degeneracy, and all these elements that Francis was mentioning. So this is sort of not fully orthogonal line, but something different. Yeah, so a quick reflection just for, just to understand that this approach kind of goes a little bit beyond most of traditional ideas that are generally used or published in the literature. You start from reaction networks, and the red pathway tells you more or less the idea of simulation dynamics or analytic approaches in smaller systems. So just try to solve the differential equations and then get to know an understanding of the dynamics through the Jacobian or whatever methods in the Strogatz book you can find. And if not, the idea is to compute organizations, get to know a sort of general landscape of where are the stable guys beforehand, and then try to do simulations around those that you already know that have all the necessary conditions to be analyzed, and not just go straight to the equations. That's the idea. And from the abstract perspective, the processes, as I mentioned before, they are collective transformations. So we have many different kinds of species in principle, and we have many kinds of potential interactions. We can describe complex interactions through pathways. You need to break this thing down, then this other thing must come in and so on. And the whole process is just representing eventually one interaction. Like in ecology, we can have the prey and the predator get together, and that creates a dead prey and a happy predator. And then the dead prey turns into food. We don't go just straight to prey is food. We can make it dead prey, and it can decompose without being used up. So we can sort of make long mechanisms as pathways. So we can explain, that's why I have these mechanisms, I think, here. And if we look at an abstract level, the languages that are used to model complex systems in general, I mentioned dynamical equations, like differential equations or stochastic equations and so on. They are normally tractable only for few species and few interactions. If you go above maybe more than 20, 30 equations, you start getting into trouble, and it's not anymore very handy. With networks, traditional networks, you can have many species, but only one type of interaction, which is the link you establish. If you establish a different link, you will have another layer of the same network, but then how to connect the layers, there is no in principle way to do that. You need to go to ad hoc methods. You don't have it in the language of networks, how to connect different layers. In reaction networks, you don't need different layers. All the layers are interwoven from the beginning. And in agent-based modeling, you have pretty much very similar abilities than with reaction networks, but they don't have a theory of what would be the stable guys after a while. So that's the, I call it that they have very poor analytic tools. They rely on simulations, and I will do like long parameter analysis and so on, and then describe which parameters fit what I want to say. But then I bring a new rule. The other team, like other office, made a same model, but with two different rules. You get to redo the analysis. There is no structural way to connect the two agent-based models, as far as I know. If anybody knows, please let me know. But in reaction networks, as I just explained, you have the Hasse diagram, you change your network, you change your system, you change your parameters, and you have a very clear analytical way to say, these differences are due to that. We can't say that in agent-based modeling. They don't have that. It's not common way of working. So then one of the interesting ideas is that we can think in algebraic terms of organizations. So I will just briefly mention, there is a lot to say, and I'm highly interested in pursue this research line. So first thing to say, I'm just gonna elaborate on the idea of the closure. So we just look at the closed sets, not the whole organizations, just the closed sets for the sake of this argument. We know that it's a necessary but not sufficient property for an organization, and thus for being an instance of self-organization. So if we look at all the closed sets in this Hasse diagram that I mentioned, we will have not all sets, of course, we will only have those that are closed. And it's interesting that we know that any set can be taken into its closure by adding the products, then adding the reactions that can be triggered by the set and the products, get the new products, then get again, and so on and so on. So you close it. And anytime that you reach this process to a fixed point, which means that you add the products and then you get the same, then you are safely in a closed set. So you can define the generated closure of any set as such, and it's unique, and it's all the minimal you can get, and it fulfills all the properties that want to have. So then we can define what happens with the union and take the closure, and the intersection and take the closure. So I just reversed the operators. I don't know why. And the join and meet, you can define the join and meet. Yeah, it's I don't know, vertical Daltonism. And then if you define these operators, that you take two sets and take the closure, two closed sets and take the closure of their union, or take two closed sets and take the intersection and the closure of that, you will notice that the structure you get fills all the axioms or properties of a lattice. And then algorithms can profit from this structure, so you don't have to calculate the closure. You can just simply know that if you take two, you will get somewhere. So as Speroni Pietro, the co-founder of the theory with Peter, I don't know really the story, you can tell us how this came up, but he developed an algorithm in 2015 to make use of these ideas. So, but the interesting thing is not so much yet for the algorithmic stuff, but to keep in mind that there is an underlying algebraic structure. What I'm interested on at this moment is that this structure, eventually, we can define a negation for it. And there are many ways to define that. Since this is very much like subsets of a major space, so the instances, the closed sets are actually subsets. There is a name for it, maybe you know, like projective. It's very similar to a projective linear structure. So when you take a set, you take the closure, and that will take you to some other place, but then you know you stay there. So it's a sort of idempotent operation, similar to the linear closed subspaces. That's the name. So I think there is a very clear connection between the algebra of closed sets or of organizations, because it can also be developed for organizations in many cases, and these algebraic ideas that are in the foundations of logic or mathematical logic. So there is a nice bridge there, but I will not go further today. Instead, I will try to get back to the idea of resilience and of all these ideas that make a system goal-directed, but take an algorithmical mindset. So we are into the business of letting the computer understand what is interesting for us. We know that a closed set is it's a necessary condition, so we can ask the computer to compute all the closed sets. That's totally doable. But because the Hasse diagram grows as the number of subsets, it's exponential growth, then we are dealing with exponential problems here. If the system is too large, then computing other organizations can be really complicated, can be really long, use a lot of RAM memory, but there is a lot of structural analysis we can do to make the computers to think or to prune many cases that we can, because of the structural properties, say this is not relevant. One of them is that there are several combinations of closed sets that are dynamically irrelevant. For example, any non-reactive species is closed because it doesn't produce anything, so it's trivially closed. So if I have a closed set and 5 non-reactive species around it, I will have 2 to the power of 5 closed sets that are completely irrelevant because it's just adding combinations of things that do not react. But the computer doesn't know that. So we need to explain to the computer that we only care about dynamically relevant closed sets. So then we must avoid such waste of computation. So we focus on the set of reactive closed sets. What it means reactive, that all the species participate in at least one reaction. And that's just one more line of code and will reduce a lot the computation. So once we get to that, yeah, there is a lot to say, so I will just mention some ideas. There is another interesting object here, which is called the synergy, that Francis also mentioned briefly, that if you take 2 closed sets, when they join, they can trigger novel reactions. So in this case, think, for example, of A and B as one closed set, X and Y as another closed set, and then bring AB and XY together. B and X will interact and will produce S, which in turn produce A and Y, which in turn produce B and X. So if we have A and B, X and Y living separately, they are stable. But if we put them together, there will be a synergetic process which makes more degenerate the system. So I'm not defining degeneracy here, but I am speaking of this idea of synergy to come up with some sort of framework to define degeneracy. And there are several interesting theorems or results that can be defined here. And actually, just to make the definition formal is not entirely trivial to make it general. So this is the general definition. That is, for time, has no point, but it's important that the sub-collections do not make the job. You need to impose that when you put the collection of things together, something new is created, and no sub-collection of that collection, when they get together, they make the job. So that's the trick. And then if you have a big closed set, can we find what are the synergies of it? How do we decompose it so we find optimally what are the synergies? How could have build it up? So then we define this notion of separability, which is, again, it's still under development. And we say that the I just make the definition for 2, the separable in 2 pieces. We can make it separable in n pieces, but separable in 2 pieces. You need 2 close reactive sets such that their union is the full set, and the union of the reactions of the union of species is equal to the reaction sets of the parts. So basically, there is no synergy here. If I take the whole set of species, I will get the same set of reactions that if I take the set of reactions of the parts separately. And the whole thing joined will create the whole thing. So in this sense, it is separable. It's important to call that the fragments or the parts of this separation can share species and even reactions. So we can separate something into parts that both have the same things, but they must be different somehow. So that's why it's imposed here that they are different. And then what is the relation between synergies and separability? Because clearly, if you have too many synergies, there is no way you can break it up, because if you break it up, you're going to miss one synergy. You break it up this other way, you break another. So there is at some point some structure that you can say, okay, something that does not fulfill this property in any possible fragmentation will be called non-separable. And what is the relation between separability and synergy? And we made this theorem, which is if it is non-separable, yeah, the relation is pretty straight. One case is that the whole system is generated by one reaction. If the whole system is generated by one reaction, this then it's not going to be separable, and we call it basic closed set. So those that you start from a reaction and you create the closure of one reaction, that whole thing is going to be non-separable. And there is another case which is very hard to imagine. I'm still struggling to do examples of this, that the system is not generated by one single reaction. And for every two parts, for every two closed sets that you take, such that if you combine them and that generates the whole, there must be a synergy. So these guys, the easiest way to think is that you have several pieces, many pieces, and every two you create, it will generate the whole thing. Every two you put the other two together and it generates the whole thing. Other two, the whole thing. So it's kind of not so easy to come up. At some point in some notebook, I have an example with like 18 reactions or something like that. And yesterday I tried to rebuild it and I couldn't. So maybe there are simple cases like Cohen-Specher theorem. It's sort of that kind of. Yeah, no, please.
I mean, the interesting thing here is, I mean, you're having two structures. One is algebraic, and the other is geometric. Mm-hmm. And then you have what Novas calls an orthogonal representation of the purely algebraic by the geometry. And the issue is that in the geometry you have a notion of independence of two vectors. So you have the basis. So I believe if you can transfer that onto the geometry, you will have problems doing that. I totally understand that this is an important issue, but I believe that if you can do that, that's an extra thing that you cannot really directly generalize to the geometry, because you will have then in the geometry, like you cannot build a three-dimensional vector space from two vectors. Yeah, you have a subset of this, but your idea is, which is very important. I mean, is to generate everything. But then my supposition is that we might not be able to geometrize that directly. It's interesting.
Yeah. No, I'm sure I did once, and when we developed this theory a couple of years ago, and we did examples and so on, but never, all it was in our whiteboard in Chile that never got a picture, and then we just wrote the articles, and so but this is, we're coming back to this, and we have now, that was Francis was mentioning, we have a software that is now able to compute all these things, and we are implementing with this, so we can just build it up like brute force like. Okay, so that was the fragments, and as I explained before, the idea of linearizing or studying from linear algebraic perspective the system, it's done this way. So if you have this reaction network, you can define each reaction as a vector that the coordinates tells you if you negatively or positively globally used up the species through the reaction, and then you can hand all these vectors and get a matrix. So that's the stoichiometric matrix of the reaction network. And then the process is a vector that is multiplied to this, which gives you a production, which is the global transformation as a collective transformation of the process, which is what I was explaining. So this is just to show that this can be clearly formalized. And what to me is very relevant is that we are not thinking directly in the dependence of the process as a function of the state, which is what in chemistry you do. So the reactions that have more reactants available will happen more, because it's more likely for them to come and get together, because they are just balls bouncing up in space. But for us, we might want to have something like I think it's Boltzmann demon or Maxwell demon. We can have Maxwell demon dynamics if we want. We can just make those events that are less likely to happen, those are going to happen. What's going to happen with that dynamics? We can target this problem, you know? So that's why I like so much to stay at the linear level, because we don't need to put so much constraints in what's going to happen. And that's the future, I think, for kind of, if you think of public policies or social systems or company development or management or something like that. There is no such a thing as, or artistic creation, which is Christian John Draco is spinning that in that way, trying to use this for artistic creation and try to come up with actions. Like this can be dancers on a stage that make certain movements. I move my arms, I move my legs, or I twist. And depending on what situation is going on, I will change and I make a choreography out of a reaction network. But I'm not going to use mass action kinetics for that. That's the point. There must be some other thing. So yeah. Okay. So now I will quickly go over this idea that I was telling, that the fragments can be perturbed when you make a perturbation in the system. So you change the state, or you change the rules of how reactions happen, process perturbation, or you change the structure, meaning I add a new reaction to the system. That perturbation will not impact the entire network per se. It might do it, but in principle will just impact everything that is interacting with. So what has a species in common? So that reaction will use that new reaction will use up some species that are available, that are in the system, and that will have some impact in those species that are affected by the productivity of this particular species. So how do we formalize that? Because we need to tell the computer, target the perturbation. So help me to do the analysis. Don't just go and simulate and tell me afterwards, okay, the simulation tells you this. We want to go to the impact at the structural level. So the first thing to define is this notion of overproducibility, which is basically to say, I mean, to read this is boring, but basically is that there is a pathway that doesn't need to use all the possible reactions, just maybe some of them. There is a pathway that ends up with more of something and nothing of the other things used up less. So you start with, I don't know, you work with ABC. You start with a certain amount of ABC and you end up with the same amount of AB and more C. So you apply a certain process and it gives you that. So if you apply it again and again and again, you will have as much C as you want. So you can generalize the notion of inflow using this idea. So overproducible species are generalized inflow, which means that the inner working of the system allows you to create it as much as you want. Of course, they might probably be dependent on the input. So whatever input I have, I can consider it as infinite because at somehow that input can be kind of coming, I don't care, it can come as much as I want. Then I can use that to create something extra and so on. It turns out that not necessarily all species are overproduced, but there is a maximal set. For every reaction network, there is a maximal set and it's unique. So there is something monotonic. There are many other things that we can say about it. And the other important entity is the non-reactive. I don't know. Okay. So the other is the catalyzer. Catalyzers are those that are used and consumed the same amount in all possible reactions. So they are just catalyzing reactions, but they are not used and not consumed. We can generalize this idea as well, but just for the sake of the argument, we call them that they have stoichiometry 0 in the reaction network. We look at them, they are never produced, never consumed, but participating. And it's of course, this maximal set is also unique. So we can just take the maximal set of overproduced species and the maximal set of catalyzers. And what do we get after? What remains to understand? We have some that are overproducing, some that are catalyzers, and the others are not overproduced. So their maximal production will be 0 because otherwise they will be overproduced. And they are not catalyzers. So it means that they are consumed and produced by some reactions. If they will not be produced by any reaction, then the system we know is not going to be an organization because those molecules are not produced. They must be consumed because it's reactive. By reactivity, you get that they must participate. So they are not produced, then they might be consumed. If they are not consumed and produced, you can make sure it's not self-maintaining. So they must be produced by some reactions, consumed by some other reactions. Their maximal productivity is 0. So it's explaining that thing. It's, in other words, they are certainly consumed more than produced by some reactions and consumed more than produced by other reactions. And eventually, they might reach the 0 productivity for the self-maintenance. And it turns out, just to make it quick, by some methods, we can identify that those within a certain large reaction network, those guys that accomplish this property of not being overproduced, not being catalyzers, they can be split into groups. Because if you start from one, you are sure that it's going to need another one. And this other one is going to need another one. And you can create a sort of loop that might be the whole set, in which case you have only one loop, or you might create the loop and end up not covering all the possible guys in this class. If it doesn't cover the whole, you need to take another, which is not, and then create the loop, and then another, and create the loop. And this can be formalized and taught to the computer how to do it. So the idea, the simple example is here. If you have an overproduced species, O here, which connects to X2, and it connects to W2, they seem to be topologically connected, but they are causally disconnected because the production of X1, X2, Y2 is not related dynamically to the production of Z2, W2, because they are connected through a species which is overproducible, which is not going to be harmed by the happening of each of the sides. So the two sides act dynamically independent as long as the overproducibility of O is ensured, which depends on the dynamical law and if it's possible or not. But if such thing is possible, we can just disentangle the two dynamics. There's no problem in doing that. And if you have a perturbation, a structural perturbation, a new something that it's Y2, we know that Z2, W2 is not going to suffer by that perturbation. So that's the important resilience element in it. That if you are able to decompose the reaction network into dynamically independent parts under some conditions, then perturbation analysis can be done much easily. And also, if you look at the abstract Hasse diagram, you will know that the whole thing of this partial order set, having all these organizations there, is just remain the same. This other part that is going to change, and that is what can change all the logical structures or dynamical possibilities. So that's our kind of mindset. So there is a theorem for decomposing organizations. And I give now Stefan, Peter, you want to talk about the...
I can, yeah.
Do you have slides?
Yes.
Can you send it on email?
Okay.
Because we need to project them from here. So that's it. If you have questions in the meantime, while Stefan sends the slides. Yeah.
Yeah, what you said about overproducible, allowing you to separate the set, it's a little bit similar to what I called the abundance degeneracy trait of if something is abundant, that in a sense makes the different parts less dependent on each other. So we need to discuss that further because it may be interesting to find biological examples of that, where something being abundant makes it that you do not need to reach it via different pathways.
Yes, it's. I was also thinking about that when you mentioned the webcam. When I said that's the webcam was just reset to the old one, so I was. Yeah, so the abundance degeneracy, right?
Yeah. The degeneracy is the idea that you make something via two different pathways. If it is abundant, then if one of the two pathways would stop functioning, you don't care because anyway it's abundant.
Yeah.
So it's a bit the same kind of thing. It kind of separates degenerate pathways, making them independent, which means if one of them just disappears through some mutation or whatever, the system doesn't notice it and won't repair it.
Yeah, what I can tell you that this, as I said before, it's good to reconsider this as not the real mechanisms for resilience, but more like a conceptual ground to start building proper definitions. And it's kind of unfortunate that because of the preparation of the symposium and so the workshop and so on, I didn't have time to present our latest research, which is some of the stuff is published, some of the stuff is ongoing, but I think I can manage to get quickly to a nice result. What's the shortest pathway? Because we got published yesterday a paper in complexity. Finally, after several months.
It was actually the first paper of our project.
Yeah.
But it was the last one to be published. All the others were published beforehand.
Yeah. So here we are working on Stefan's slides. If anybody in the audience have questions as well, please just open your microphone. We have like 2 minutes remaining for questions.
I have a question concerning fixed points. You made fixed points. Is this, does this include also delayed fixed points? Fixed points like after 2 cycles?
Yeah. Like periodic orbits,
Yeah.
yes. Well, Stefan is the real expert in the relation between chemical organizations and limit sets. There is an article that is, there are some subtleties at the edges of the phase space. When you go towards 0, there are certain subtleties because continuous dynamics and discrete dynamics, they behave differently. So then it's when it becomes like really complicated. So we try to not really focus ourselves on getting deeper and deeper into that, but to remain at a more abstract level. So I will just quickly show this picture because this is a model we did, Francis developed, and then we analyzed it with our methods, with this decomposition of organizations and so on. And we show that this, I guess you can see clearly here, right? And then I share Zoom screen so everybody can see this. So guys, I'm going to show very quickly a diagram here. So this diagram, what it shows is a farm, a model of a farm, which is given by these reactions. First, I will show the reactions. So these are the reactions. Sorry, this, like water comes from the river, then grass and cows and infrastructure, and water brings milk, cows, and dung and infrastructure. Dung creates worms and fertilizer, and all these reactions of this kind just expressing how a farm works. The farmer can sow eggs, can sow milk, grain, straw, chickens, worms can escape, infrastructure runs out. So we have like a sort of narrative of how farm works with money, with elements, and with income things and so on. Of course, cows are not dying here. We have them, we are thinking of a time scale which is smaller than the expected lifetime of cows. And then we get to some particular organizations. So this is the Hasse diagram reduced to the organizations. It only has four. Grain and chickenless farm, grainless farm, and chickenless farm. So we have like, that's the explanation, which of course these are different subsets. And then we work with the full thing, with the full farm, and establish 2 different ways of operating the farm, which means 2 different ways of running, using up the water, using up the cows, and creating money or not. And one of the ways is like optimizing the generation of money, profit. And another way is not optimizing the generation of profit, but optimizing the generation of everything that can be overproduced. The big difference, so the green guys in these pictures are what is going to be overproduced depending on how you operate the farm. And then the cyan and magenta molecules are the two fragile circuits, the decomposition of those things that cannot be overproduced, separated into two groups. So in the first case, there are all these things are sensitive, and there is another collection of sensitive things, which is just the infrastructure. In the other case, you have these three things that are sensitive here, and these other three things that are sensitive there, but they are not connected, because the dynamics of overproduction separates their productive processes. And then we make different, like a stochastic or statistical analysis for perturbations to show, this maybe it's a relevant, just quick mentioning. And we show that the way in which the system responds to perturbations is completely different. If you operate the network just overproducing money, because of this all other objects are fragile. If you incorporate a mouse, for example, that eats the grain, the mice eats the grain, and that makes collapse the whole organization into something very small, or even destroy the ability of the farm to sustain. Whereas in the other case, it will just break down the part that produces grain, and all the other productive processes will remain untouched, because you ensure by this overproduction and so on. So
it's a nice model for rationalization. If you rationalize all your processes to maximize the profit, it becomes much more fragile. So if something goes wrong, it's more likely to break down as a whole. If you don't maximize your money, then you can be more.
This is actually how it looks. The mice, when you incorporate the mice in the system, this is what happened. Like all these arrows that get disconnected after a while. And when you introduce the mice in the second case, everything can still sustain. Of course, you have a low in your production, but the system can keep running. So, and we have kinetics for the simulations, which is not the mass action kinetics. It's looking like, but I don't want to tell details, but we develop another way, which is more like trying to set up in the mind of a farmer who wants an idealistic operation of the farm. So the farmer wants the farm to operate in a certain way, and with the resources that it has, it will try to operate it in this way. So that's what we devise as a kinetic law, which is nothing related to chemistry. Okay, so Stefan, I'll give you the